Guadalupe Mountains stand like an island in the desert, a mere fragment of one of the largest fossil reefs known to man. Rising over 1,000 meters above the desert floor at El Capitan, on the border of Texas and New Mexico, this ancient reef, the Capitan Reef, enables us to look back at the intricacies of reef-forming processes in the geological past.
The escarpment running off into the distance behind me is the front of the Capitan Reef itself. Nowadays, much of the area has been converted to national park so that people can enjoy the beauty of this desert region. In historical times, the area was inhabited for many thousands of years by Indians, and then only more recently the settlers came here. But the story of the Capitan Reef goes back a lot further, some 230 million years, to the Permian. Now, you can tell a lot about how the reef came to be by looking very carefully at the rocks and interpreting these in terms of the processes going on today in marine environments. This is essentially a uniformitarian approach, where you assume that processes that were operating in the geological past are the same as processes that you can see operating today.
So it's helpful to start by taking a look at the large-scale features of a modern reef. There are many different kinds of reefs, but the long tropical barrier reefs of today are the most similar in their general layout to the Capitan Reef. In cross-section, a modern barrier reef system can be divided into three basic regions. There's the reef itself with its crest at sea level. In front of this, there's a forereef zone of debris that's spilled down from the reef, forming a submarine scree sloping off into the basin. In most modern barrier reefs, the reef faces onto an open ocean. And behind the reef, there's a back reef zone of lagoons in which water depths rarely exceed a few tens of meters. On the reef itself, corals and many other associated organisms thrive in the clear, warm water that surges over them from the open sea. Turbulent water that's well aerated and stocked with the planktonic organisms on which the numerous polyps of these coral colonies feed. Here, the calcium carbonate from which corals and other shelly organisms construct their skeletons is in plentiful supply. The coral's growth also benefits from the light because of the photosynthetic activity of symbiotic algae in their tissues. Some corals, like these sea whips, are flexible. But most of the corals, like these elkhorns, produce strong, rigid structures. On the ocean side, the reef front plunges down into much deeper water. A rich diversity of rather different organisms also live down here amongst the reef debris. Behind the barrier complex of the reef, the more sheltered environment favors the accumulation of fine-grained carbonates. However, because of the changeable and often high salinities here and the monotonous topography of the lagoon floor, the communities often have rather few species that can tolerate these fluctuating conditions. How close are the parallels between a modern barrier reef and its neighboring areas and the fossilized Capitan Reef and its surroundings? In other words, is it possible to make a simple uniformitarian comparison? Unlike a modern barrier reef, the Capitan was built mainly from lime-secreting algae rather than corals. The fantastic thing about the Capitan is that not only is it well preserved and beautifully exposed, but it has preserved its original topographic form, much as it would have been beneath the sea in late Permian times. This ridge was a linear reef lying along the edge of a submarine shelf, adjacent to a deep marine basin, which is now just the flat dusty plain in the foreground. The shelf now forms a high mountainous plateau region in the southeast corner of New Mexico. The Capitan runs along the edge of this shelf, and from other outcrops and from boreholes, it's possible to deduce that this reef isn't really linear. It faces into and partially encloses what used to be a deep marine basin. This basin now occupies about 10,000 square miles of West Texas. The topographic profile of the Capitan Reef is similar to that of a modern barrier reef, with a high shelf area separated from a basinal area by a massive reef zone. We'll be concentrating on the rocks produced only during the last stages of reef development. On the basin side are a series of beds of reef debris. Behind the reef are thinly bedded limestones, dolomites and sandstones. The reason why the whole complex has been so well preserved is that eventually in the hot climate the water began to evaporate more quickly than it was replaced, and vast amounts of evaporites were deposited over the reef. Over 200 million years later, the perfectly preserved Capitan Reef was exhumed by erosion. Remnants of the evaporite that once covered the basin and the reef are still preserved as small hillocks around the edge of the reef. After the reef was exposed, subsequent erosion produced a series of canyons cutting into the reef escarpment, and one in particular, McKittrick Canyon, provides us with an excellent cross-sectional profile through the main structure of the reef. High up in the back of the canyon are the bedded strata which built up behind the reef in shallow water. The large cliffs high above the mouth of the canyon form the massive reef complex itself, and beyond that beds of broken reef fragments sweep and curve down into what was once the deep water basin.
Now there's a pretty clear distinction between the more or less flat strata of the back reef on the left, massive limestone of the reef itself in the middle, and the foreslope strata which are dipping down towards the basin on the right. And that's pretty much the sort of pattern you'd expect to find if you took a section through a modern barrier reef. So the analogy between ancient and modern seems to be holding up, in broad terms at least. But what about the reef rock itself? How does that compare with its modern equivalent? What I'm walking across is part of the ancient reef itself, preserved here as massive limestone. In most places it's been heavily recrystallized, so you can't really see what's going on. But here and there are patches where the fossils are very well preserved. For example, this is a section across what would have been a large mound-like sponge. And down here are a number of sections of what would have been leaf-like algae projecting up from the reef surface. These, with other organisms such as bryozoa, grew up from the reef surface to create a kind of framework for its growth. Meanwhile, everything was being densely encrusted by these successive light and dark bands down here.
Under the microscope, these layers are even more obvious. The dark bands in thin section are layers of calcareous algae, whereas the light brown areas are inorganic crystalline cement formed from calcium carbonate, rather like the fur in your kettle. This intergrowth of algae and calcium carbonate implies that the cement was precipitated on the reef surface as it was growing. In addition, there's quite a bit of fossil debris derived from organisms like this gastropod, once part of the abundant life which lived on and around the reef. But is it possible, from just looking at the fossils in the outcrops, to envisage what this reef would have looked like back in the Permian? The variety and abundance of life on and around the Capitan Reef was probably just as great as it is around a modern coral reef. This isn't a modern reef, In fact, it's a life-size reconstruction of part of the Capitan Reef at the Permian Basin Petroleum Museum in Midland, Texas. The basic fabric of this reef was similar to that in modern barrier reefs, but with rather different actors in the same roles. In striking contrast to modern reefs, there are no large framework corals. However, a projecting framework is formed by various organisms, such as these large tubular siliceous sponges, and calcareous sponges are particularly abundant. Fern-like bryozoans are also very common, as are the distinctive crinoids, commonly known as sea lilies. These, together with a variety of brachiopods and other organisms, also provided debris which was eventually incorporated into the reef rock. So did this reef grow in the same kinds of physical conditions as a modern tropical barrier reef? Let's first of all consider the salinity. The organisms of the reef are strikingly varied, but there are a number whose living relatives are only found in marine water of normal salinity, such as the crinoids and articulate brachiopods. Otherwise, of course, the abundant algae show that the water over the reef was well lit. So it's reasonable to assume that, as with modern tropical barrier reefs, the Permian Reef was bathed in open, well-lit seawater. But what about its resistance to wave surge? Most of the framework organisms in modern reefs, like these elkhorn corals, rely on strength and rigidity to build up the reef. They protrude right up into the well-aerated zone of wave surge. But occasionally, though, they do break off in storms. A few kinds of living corals take up the wave surge by being flexible. And so the question we need to ask is, did this reef have the same sturdy framework that characterizes modern tropical coral reefs? Do you imagine that the main framework organisms here could have withstood battering by waves? Many geologists now believe that the answer is no, and this means that the reef would have grown below the level of wave action, more than, say, about 10 meters deep. Towards the basin, in front of and below the main reef complex, are large talus slopes of reef debris which gradually curve off into the basin where the water was at least 600 meters deep.
This knobbly bed of limestone here is a lens of what would have been loose reef debris that slithered down the slope in front of the reef and came to land on the finer grained sediments at the foot of the slope. Now, those finer grained sediments have been compacted a great deal more than the limestone, so this is why they appear to be bent around its base. Now, we're some 600 meters down from the level of the reef itself, but even down here there's still an abundance of large whole fossils.
Some of these fossils have been transported in, but others represent the in situ fauna. The fossils are quite easy to see because they've been silicified and are slightly more resistant to erosion. There are plenty of sponges and brachiopods and even occasional crinoid ossicles. This fossil-rich debris is very reminiscent of the upper talus slopes of modern reefs.
A short way further out into the basin, the fossils are far fewer and smaller. In this small cliff of limestone with chert nodules here, they're restricted to certain horizons. For example, there are a number of small entire brachiopods which may well have lived down here, and otherwise small fossil fragments which probably drifted down from higher levels.
And as soon as you get further away from the reef, out into the basin proper, the scenery flattens off quite dramatically. The reason being that out here the lower lying strata are almost horizontal and there's very little erosion to form valleys and cliffs.
In this kind of flat terrain, your only chance of a decent outcrop is the occasional road cutting such as this. I'm about 5 miles out into the basin, and already the beds here are much thinner and more or less flat. They're made of fine muds and silts, and they're extremely finely laminated. Of course, this means that they haven't been churned around by burrowing organisms. Moreover, body fossils are extremely scarce, just the occasional sponge spicules, for example, which have been drifted down from higher levels. So life out here on the basin floor must have been very scarce.
But there are a few unusual features out here, like these large blocks of reef debris. It's possible that earthquakes were responsible for these blocks tumbling down from the reef. The basin surrounded by the Capitan wasn't completely enclosed. There were a few openings to the open ocean to the south. As a result, well-aerated oxygen-rich water was brought in and circulated around the upper part of the basin. The general lack of fossils away from the margin of this marine basin suggests that the deeper water was anoxic. There was no oxygen there at all. The surface currents failed to mix in with the deeper water. The only fossils out here drifted in from the margins or were from organisms which swam around near the surface. When they died, their remains sank over 600 meters and landed in thick black mud at the bottom. We've taken a look so far at what happens on the reef itself and on the deep water side of the reef. But what happens on the submarine shelf behind the reef? Here the water was shallower, and there are bedded strata mainly of carbonates and evaporites, which thin dramatically towards the ancient shoreline, which was still at times up to 50 miles or more further into New Mexico. From a distance, differences in these shelf strata are not clear, but on the ground it's a different story.
I'm now about 30 miles further along the escarpment to the northeast from McKittrick Canyon, and I'm on the very back part of the reef. The massive limestone of the reef here consists of patches of bound limestone with intervening areas of coarse shelly limestone, which would originally have been well-winnowed shell sands and gravels. So clearly this back part of the reef was rising up into very shallow water where there was abundant wave current activity. But what about further up on the shelf, immediately behind the reef?
Here the small areas of bound reef rock gave way entirely to the shelly sands and gravels. The rock formed here is a grainstone, a loose aggregate of well-washed carbonate sands and gravels. In this thin section, it's composed mainly of fossil fragments, surrounded by a later cement. And there are also plenty of nearly complete portions of crinoid stems. Because they're not very broken up, it's probable that the crinoids lived close to where they're found now. Crinoids will only live in seawater of normal salinity. So even though we're behind the reef, this outer part of the grainstone belt was evidently washed with open seawater. The grainstone is economically the most important horizon, where the reef is buried beneath evaporites. Oil produced from organic rich layers in the sedimentary basin migrated into the grainstone belt, which acts as a reservoir capped by the non-porous evaporites. Oil seepages in this area were known to the Indians and to pioneer settlers, but commercial extraction didn't start until 1921. There are now over 10,000 oil wells.
The cities and the bright lights, you can't leave them all behind. Head for the open spaces where the clouds go rolling by. It's lonesome on the
Further to the northeast, the Capitan Reef underlies part of the enormous Permian Basin, and over 96% of the oil in this basin comes from strata of Permian age.
Hello there. Could you fill it up, please?
Is there?
Unload
Ready?
it, please. Yes,
Ready.
thanks.
Texas accounts for over 40% of the US oil production, and the Permian Basin alone produces more than half of this. over 600 million barrels of oil each year. Even further behind the grainstone belt, you move on to what was originally the highest point of the whole reef complex. Fossils back here are scarce, like this gastropod, which could tolerate high salinity. These outcrops contain a variety of rock types, including these laminated limestones, which were formed by algal mats. The small cavities in the crinkled layers are believed to be fossil gas pockets, indicating an intertidal setting. So the area had variable salinity and was also subaerial sometimes. Behind this barrier were shallow lagoonal waters, which evaporated quickly to produce highly saline water, which deposited evaporites. These became buckled as the evaporite crystals grew within the sediments, sometimes in small clusters. We're now in a position to compare the original profile of the Capitan Reef with the modern barrier reef. In the Permian, the wave energy was dissipated over the grainstone belt behind and topographically above the reef. The barrier of islands and shoals was some way behind the reef itself. This is quite different from a modern tropical barrier reef, where the wave energy is dissipated on the crest of the reef itself, which grows up into much shallower water. So even though the modern and the ancient reefs have broadly similar structures and profiles, in detail there are important differences. Even before the sediments that accumulated above the Capitan Reef were stripped off, groundwater percolating through the reef dissolved enormous cavities. These caverns are a typical feature of limestone areas. I'm now right down inside the Capitan Reef itself. These caverns, the Carlsbad caverns, represent just the latest phase in the long history of this spectacularly preserved reef system. The age of these structures is to be measured in thousands of years, compared with the 230-odd million years of the reef itself. But that's another whole story. What we've attempted to do in this program is to build up a picture of what the reef was like while it was growing, based not on a simple comparison with any one modern reef system, but rather by piecing it together from our detailed observations of the rocks and their relationships with one another, based on what we can see in a wide variety of modern reef and non-reef environments.
reading